So here we've got a code very similar to the one we saw last episode, where we have a frequency, a wavelength, amplitude, and a phase. Only this time, we're doing this for two different waves. So I've got frequency 1, wavelength 1, etc., frequency 2, wavelength 2, etc. And then when I come down here to the wave creator, all I have to do is have two different waves, right? So I've got a wave 1 and a wave 2, and two wave functions, one to take care of wavelength 1 and frequency 1, one to take care of wavelength 2 and frequency 2. And then down here, we just animate both the waves, wave 1 and wave 2. And then what we're doing, we're adding in this part where we have the total wave. Now you notice total wave doesn't get its own wave function. Its y coordinate is determined by the sum of the other two, so wave 1 and wave 2. So in the animation window, when I run this in just a second, we're going to see three different waves. One of them is going to be red, that's going to be wave 1. One of them is going to be blue, that'll be wave 2. And the other one will be the total wave, that's going to be green. So red plus blue equals green. Let's take a look at that over here. Look, I even gave you a reminder over here, green equals red plus blue. So if I look at this, let's take a look at the red wave first. The red one has a frequency of 2 and a wavelength of 1.5. So the red is a pretty narrow wave. It's going across the screen. The blue one is a much broader wave. It's got about twice the wavelength of the other one, and it's got about half the frequency. So when I look at this, these two waves, red and blue, do not line up with each other, and I get this really cool looking green wave. And you might say, oh, that's not a sine wave. No, it's not a sine wave. It is a combination of two sine waves, or a combination of two cosine waves, really. But sine and cosine are the same thing apart from a phase. But this thing is still a wave. This green thing is still a wave because it is a repeating shape that moves forward in space. Like, that's really the definition of a wave. You can have a wave of any kind of shape, not just sine or cosine. And you can play around with this. You can do a lot of different things with this. So for example, here we've got some parts where the waves are really adding together. So like here at these troughs, these two waves are really adding together. But then at this point, you've got blue going up and red going down. And so green just kind of dips down to the middle here. So those are examples of what we call constructive interference and destructive interference, because you're either constructing a larger wave or you are destructively canceling the two waves out. Let's take a look at a clearer example of that. So let's try giving the waves the same frequency and the same wavelength. 1, 1. Let's even give them the same amplitude, and in fact, let's even give them the same phase. So we've got two identical waves now. Red and blue are two identical waves. And so they sit right on top of each other. We can't even really see the red because it's there right behind the blue. I wonder if I rotate this around. Nope, blue is completely subversing the red. Well, anyway, they combine to be an even bigger wave, this green up here. And I don't like how that's getting really choppy. So let's actually decrease the dx a little bit. Let's make it 150 points instead of 200. There we go, that's a little bit smoother. The point being that the red plus the blue gives you this really big wave here on the green. You can even get that if their waves are a little bit off from each other. Let's suppose we move the red forward in phase just a little bit. I guess it moves it backwards, but anyway, point being, let's change its phase by just a little bit. You can see that the red and blue are separated just a little bit now. We're still getting pretty constructive interference. Let's try a half. Remember, these are in units of radian, so think of this as a trip around the circle, being 2 pi. So again here, red and blue separated by just a little bit. We still get constructive interference, right? We're still getting bigger peaks. Now, if I keep doing that, let's move on to, let's say, 1 radian, separating them. Now my green peak is starting to come down a little bit because my red and blue peaks aren't quite lining up with each other. Let's see, 1, we're getting pretty close to pi over 2. So let's see what happens. So when we have pi over 2 separation, that's the difference between a sine curve and a cosine curve. So you can think of one of these as being a sine, one as being a cosine. I'm still getting constructive interference, but it's not nearly as dramatic as what we saw before, right? I'm not getting 1 plus 1 equals 2. I'm getting 1 plus 1 equals about 1.5-ish, something like that. Now let's try moving this on. Let's go to 3 times pi over 2. So we're not quite to, oh wait, excuse me, no wait, 3 pi over 4, that's what I meant. Let's go, we're approaching pi here. Let's try going to 3 times pi over 4. You can see here, they've separated enough to where we're actually getting lower than we had before, because right now you can think of this peak as coming from these 2 points right here where they're crossing with each other. So we're not getting nearly as strong of a wave here. And now let's see what happens when we go all the way over to pi. So when these two are separated by pi, anywhere I have a peak on the red, I have a trough on the blue, and vice versa. They completely mirror each other, and so their points completely cancel each other out when we add. So whenever you have two identical waves separated by a phase difference of pi, the waves cancel out. Your total wave is flat. And really, this is the way noise-canceling headphones work. Let's say the red is the incoming sound. Your noise-canceling headphones pick that up on a microphone and then emit an identical wave in terms of the blue that is identical, except it's shifted by a phase factor of pi, and so that cancels out the noise. So that's where your total sound inside your noise-canceling headphones gets to 0. And then, of course, you can decide that you don't like that. You can decide to have one of the waves win out over the other one. So I can change the blue wave's amplitude. And so blue is always stronger than red. So green follows blue, but it's not quite as big because we've still got a tug of war going on between them. And then, of course, you can have more fun with this. You can give them the same amplitude, the same frequency, but then give one of them a different wavelength, for example. So this is where you might have two sound waves of different wavelength going on. And that's where you really start to get some interesting things, because here you've got red and blue are moving at different velocities. That's interesting. Hopefully in the previous video you discovered how you determine the velocity of a wave. And so the green wave's profile is not consistent, right? It's doing this little undulation thing. And so this is where you can get some really interesting stuff happening with waves. Now, normally waves move through a medium with the same velocity, so you should probably keep them at the same velocity. But this is just some of the cool stuff that you can get with waves going on. So anyway, I hope this is a fun activity for you. In the next video, we're going to look at when we add many waves together. And so the activities at the end of this video will help prepare you for that. Thanks so much for watching. I'll see you next time. Bye-bye.